Hello from Tulsa, Oklahoma. Okay, first of all, I want to thank Christian Constanda for once again encouraging me to participate in this conference. This year my talk is titled Optical and Geometric Parameter Extraction for Photonic Integrated Circuits. Okay, so photonic integrated circuits are miniaturized optical systems that are created in thin film transparent materials. These are often described as optical systems on a chip. So when photonic integrated circuits are designed, they are made of specific types of materials, and they have specific dimensions, size, length, width, height, etc. Okay, but however, as with any manufacturing process, there can be deviations from the design or the ideal, and particularly with emerging technologies, which is certainly the case here. So what I'm going to describe today is our method for extracting optical and geometric properties from photonic integrated circuit elements post-fabrication. Okay. Now, the most fundamental building block of photonic integrated circuits is the waveguide. It allows light to move from place to place on a chip. So all of our photonic integrated circuits are currently manufactured at AIM Photonics Foundry up in upstate New York. This is a snapshot from their design guides showing the user, the types of waveguides that are available to build their photonic integrated circuits from. I've showed here is a built 300 millimeter wafer. Each one of these would represent an optical system, and each one of the lines in there would represent an optical waveguide. So, what are waveguides? I think most of us are familiar with this type of waveguide structure, where we've got a piece of glass surrounded by air, and in this case a cylindrical cross-section. Fundamental physics behind waveguiding is that we've got a material where the light travels relatively slower, surrounded by a material where it would travel faster. Okay, the speed of light in a material is characterized by its index of refraction. So it's the speed of light in a vacuum divided by the index of refraction. So we need slow material surrounded by a fast material, or in the language of waveguiding, you have a high index core material and a low index cladding. Now, the waveguides can have nearly any size or nearly any cross-sectional shape or size. The example I showed on the previous slide was a circular cross-section. For photonic integrated circuits, we're usually dealing with rectangular, trapezoidal, or some related structure to that. Okay, so to understand the parameter extraction process, I want to introduce you to the fabrication of photonic integrated circuit waveguides. So first, we start with a silicon wafer. It's the same type of silicon wafers that you would use if you were going to make electronic integrated circuits for your computers or cell phones. Okay? And on top of this silicon wafer is grown a thermal oxide layer, silicon dioxide, which has an index of refraction of approximately 1.4. Okay? Now, on top of that, a silicon nitride layer is deposited. We use silicon nitride because for our particular applications, we want to work in visible wavelength range. Okay, so and silicon nitride has an index of refraction of around 2.0. Okay, so the oxide layer is about 4 microns thick. The silicon nitride layer would be hundreds of nanometers thick. Okay, and this is the layer that we're going to pattern using optical lithography all of our photonic integrated circuit elements. Okay, for example, this is the picture I showed earlier. You would end up patterning all these different structures in that silicon nitride. But for this example, I'm going to use a very simple patterning process. Let's just imagine we used optical lithography to remove all the silicon nitride except for in a single strip along from one end of the wafer to the other. So if I zoom in on this, what I'd see is now we've got a silicon dioxide base and a silicon nitride strip waveguide. And this is just roughly the dimensions of the waveguides we'll be showing data for in this work. Okay, the last step of the process, the fabrication process, is to cover this entire structure with a top oxide layer. Right? So what we have is now optical and geometric parameter extraction is the determination of the refractive indices and the dimensions of the waveguide after fabrication. Okay? And we do this by measuring the speed of light along the waveguide. And then we solve for the parameters of interest, the thickness, the width, and the material indices using an iterative inverse method. Okay, so how do we measure the speed? In order to understand the speed, we've got to understand modes. Okay, so imagine, just like with the fiber optics, we have to send light in one end and it propagates along that waveguide. We have the same situation here. We're going to send light in one end of our waveguide. And what does it look like when it's propagating through these materials for this size of structure? Okay, so I'm going to take this and turn it on its side and just look at a cross-section. So we've got a silicon nitride core with a silicon dioxide cladding all the way around it. So we can use a finite element method solver to determine where the light is traveling as it travels along the structure. And this is what we get for a particular example of TM, which means transverse magnetic. So this is I've written horizontal polarization there. This should be vertical polarization, so it means transverse magnetic. So the idea is we've got obviously have some of the light in the cladding and some of the light in the core. So it can't possibly travel with a phase speed that is the core or the cladding separately. It's got to be some combination of the two. And so we define it as the effective index of the waveguide material. It's got to be somewhere between the cladding and the core, and it would all depend on how much of the light is in the core versus how much of light is in the cladding. Okay. So the parameters that determine that are what is the core index, what is the cladding index, what's the width, and what's the thickness. You can imagine that if we change any one of these, the relative amount of light in the core versus the cladding is going to change. We talk about the effective index of refraction being sensitive to these four parameters. Okay? And these are the four parameters we're going to extract by measuring this ineffective, or fundamentally, the speed of the wave, the speed of light as it's traveling down this waveguide. Okay, so here's parameter extraction basics. We've got actual values that of the fabricated waveguide: width, thickness, core index, and cladding index. And we've also got design or expected values of those same values. Okay? And what can we measure? Like we talked about before, that's ineffective. We can't measure we don't have access to any of these other parameters. Okay, so we can use the same finite element method solver that we used before and calculate what an expected value of our index or effective index is, and then compare that to our measured value and define what we call an error. Error in the effective index, which would be, of course, dependent on the error in all the parameters. So what we can do is use the same FEM solver again to determine how sensitive each one of the parameters is, how sensitive, the effective index is on each one of these parameters. So just as an example, I define them as beta. So the sensitivity Jacobian this element would be, what's the rate of change of the calculated ineffective as I change the core index. So that'd be beta core, I'd have a beta cladding, and beta width, and beta thickness as well. So I can take this ineffective, the measured ineffective, and say that it's in the multivariable linear regression, saying that it's equal to the ineffective of my nominal ineffective plus each one of these terms. Okay, so what we've set ourselves up a one equation, four unknowns problem. Okay, so we solved that issue by measuring the same waveguide with both TM polarization and TE polarization. Because of the fact that they're asymmetric waveguides, they give different ineffectives for those two different polarizations. Then we choose two different widths and then measure the same TE and TM. So we do these 4 measurements, okay, then jump into the FEM solver again and calculate all the corresponding beta factors. They're going to be different for each one of these each 4 of these waveguide structures. Because if we're really small, we're close to the wavelength of light on the width, and we change it a little bit, that's going to be a big change in the effective index. But if we're already huge, much bigger than the wavelength of light that's coming down, changes in the width aren't going to matter at all. So each one of these will be different for the 4 different waveguide measurements. Okay. So what we have here now, since we've chose 2 different widths, we've set up a situation where it's a little bit not ideal, is that we've got 4 equations and 5 unknowns, because we've got 2 different deviations from the width. But if we make the approximation that the deviation from width is for the one waveguide width and the other waveguide width are going to be approximately the same, we can make this a very simple and straightforward 4 equations, 4 unknown problem. Okay, which of course, as I mentioned before, we're going to use an inverse method. We're just going to take this situation, take this sensitivity Jacobian, and take the inverse of it and multiply both sides of the equation by that inverse, and from that we arrive at values of our deviations from nominal, at least our first iteration. So we then, if it were truly a linear system and all these parameters, then we would expect that we would converge after one go, but in the end these are not, it is not linear in all these variables. Okay, so what we end up having is we update the parameters, we then recalculate the effective indices, that we expect, and compare them to the measured values, and then iterate. Okay, so typically if you're far off the first, if you're for one iteration, or if you start out with the design values, you might take 4, 5, 6 iterations to converge to an acceptable value of errors compared to the measure. Okay, so that's our parameter extraction process. Okay, so what I want to do is show you next is it's in use. How do we actually measure the effective index and the speed of the waveguide? So we use interferometry. So basically a Mach sender interferometer, and we take a single. Look at this particular one. It comes in a single waveguide. We split it into 2 waveguides, and they then recombine it back into the same waveguide again, and there'll be some path length difference between the 2 arms. So when it comes back together, they'll interfere either constructively or destructively, depending on the wavelength and the indices of refraction, or the speed of the wave down these arms. Okay. So here's an example of we send in a tunable light source, and this between 1240 and 1380, and what we see is a constructive interference, destructive interference, constructive interference, etc., which the normal, you learn about this in literally physics 2, where you have optical path length differences equal to either integer or half integer number of wavelengths. You get minima and maxima. You can easily, once you've identified your minima and maxima here, you can come up with an effective using this formula, and then fit it to a line. Okay? So then we, typical procedure, we then pick somewhere in the middle of the wavelength range where we can expect our best fit to the data, so we have the smallest uncertainty in our value, so we pick off at 1300 in this particular case. All right, so then you do these same measurements for each of the 4 waveguides, and you've got your 4 measured index of refractions at a particular wavelength. And you go through the parameter extraction process. Okay, so we give you one example. This is recently presented at last month at the conference on lasers and electro-optics. Okay, we want to look at it's called wafer A in this example. We use a standard, it's called a process of record. It's an AIM photonics foundry. It's a silicon nitride only passage NPW, which is multi-process wafer. But my point is, this is the one that should be repeatable at one time after the other. It should be the same. So if we take a 300 millimeter chip and I look at a particular tile, in this case 40, and I do the parameter extraction at 700 nanometers, I get excellent precision in my measurements. Okay, the two design line widths here are 400 and 800. So the line width, since we are using two different widths, we call a line width bias. So this means if it was 400 nanometers design, we're about 40 nanometers less than that, or 360 is what it actually comes out to be. Okay? So to show you the value of this, if we go from, what we wanted to do was show going from process to process. We might make this POR, process of record, in May, and then another one in June, and another one in July. How do they differ from each other? Okay, so this is 4 different wafer-to-wafer variations for the process of record, and what we see is fantastic agreement for the index of refractions for both silicon nitride and silicon dioxide, and then we see some variation in the thickness and the line width bias from run to run. Okay, and this is exactly what we would expect from knowing the process. The silicon nitride and silicon dioxide are grown by known techniques. Okay, so LPCVD and PECVD, both chemical vapor deposition processes. Okay, but so the material index should be pretty rock solid from one run to the other. What you have a variable process is the optical lithography. Okay, and also the actual growth thickness, because that would be very, very dependent on, obviously the time of deposition, that sort of thing. So, just one example of our uses of parameter extraction. So, in summary, I reviewed our parameter extraction method based on Mach-Zehnder interferometer measurements. We observed excellent consistency in material index from wafer to wafer in the same process at photonics, but also observed width and thickness variations as expected from wafer to wafer in the same process. So it's extremely valuable to get feedback to the foundry about this this process, and that is really in its youth in creating photonic integrated circuits. So anyhow, we'll say that, and here we say thank you very much for your attention.